Dr. Bitansky, he is with us here, and he is a member of the faculty of Tel Aviv University. He is also at the Blavatnik School of Computer Science, and he's a member of the Checkpoint Institute Information Security. He received his PhD from Tel Aviv University in 2015, and before he was in MIT, and his focus is theory of computation at large and cryptography in particular. So Dr. Bitansky, please, the stage is yours.
Thank you, Yaniv, for the introduction. Let me share my screen for a sec. Okay. So hi. So I want to tell you today about zero-knowledge proofs against quantum attacks. And in order to motivate zero-knowledge proofs, I would like to describe a conversation between two mathematicians, Paul and Vincent. And it goes as follows. So Paul claims that he had proved a very famous mathematical conjecture. And his friend Vincent is, of course, somewhat skeptical and says, well, if he proved it, then show me the proof. Now, the problem here is that Paul is facing a dilemma. He's sort of afraid that if he'll show Vincent the proof, then Vincent might go ahead and steal it and get all the glory. So what can he do? So zero-knowledge proofs suggest a solution for this. And what zero-knowledge proofs are is basically a protocol between a prover and a verifier that allows to prove things about secret information without actually revealing this information. In fact, the verifier is not going to learn anything beyond, of course, the fact that the assertion is true. And this is really a miracle of cryptography, and it sounds very different from the kind of proofs that we're used to, which would naturally involve disclosing this secret information. And when you think about it, verifiability dilemmas, like the one that Paul faced before, are really all around us, and we're not so hypothetical. So, for example, to prove that we qualify for, say, a loan, we have to disclose personal information. Same goes for regulation of financial institutions. And this also happens in larger scale. So we've been talking about blockchains. And let's say that you want to prove the validity of blockchain transactions. For that, you will probably also have to expose private details about these transactions. And there are many more examples. And zero-knowledge proofs really have the potential of solving all of these problems. And they've been around for quite some time now, almost 40 years. But have so far mostly had an impact on theory of cryptography, computer science. But in recent years, people have really come to realize that they can actually solve all of these very real problems. And there's now great investment in developing appropriate zero-knowledge proofs. Now, what I want to tell you today concerns quantum attacks. So you've probably heard that the race toward a scalable quantum computer is advancing. And while we're not there yet, both industry and governments are pouring great amounts of money towards this. And if this indeed happens in the foreseeable future, it's going to present a great challenge for cryptography. And why is that? So for once, if you think about quantum adversaries, then they're algorithmically stronger. They can do things that classical adversaries cannot do, for example, factor integers. Beyond that, we have to completely change our adversarial models because quantum adversaries may interact with systems in a completely different way, for example, in quantum superposition. And the last thing is that our techniques for analyzing cryptographic protocols no longer apply. And this is due to essential differences between quantum information and classical information, and we'll see an example of this soon. Okay, so when I speak about zero knowledge against quantum attacks, my focus is going to be on the following. So I want to design protocols that could be executed by plain folks like you and me. Okay, so the honest protocol is actually classical. But what we want is that in terms of security, it could resist even quantum attacks. In particular, even if the verifier is quantum, it shouldn't be able to learn anything from the proof. Okay. So here's what I want to do in the rest of this talk. I want to give you a glimpse of how zero-knowledge protocols look like and how we typically argue that they reveal nothing. And then I'll tell you, please give you a hint of what is difficult when you're dealing with quantum adversaries. And finally, I'll tell you a word about the sort of problems that we can solve and those that we cannot solve looking into the future. Okay. So to give you some idea of how zero-knowledge protocols look like, I'm going to describe a toy protocol for proving that the Sudoku puzzle is solvable. So if you've never seen a Sudoku puzzle, then it basically contains a bunch of squares. And initially, you're given some hints. And these are just numbers between 1 to 9 assigned to some of the squares. And your goal is to fill out the rest of the squares, the blank squares. And what you want to make sure is that if you look at every row here, then it will contain all the numbers between 1 to 9 exactly once, what we call a permutation. And this should actually also hold for every column and every such subsquare. Okay. Well, look, I've spent a couple of hours yesterday solving this specific Sudoku puzzle. And now I would like to prove this to a verifier. But of course, I don't want to give away the solution. You know, there's actually a prize here, and I want to claim it for myself. So here's what I'm going to do. I'm going to think about these boxes as cards. And first, I'm going to flip those cards that I filled myself so that the verifier will not be able to see my solution. Now I'm going to let the verifier into the room. And I'm ready to start convincing him that behind the flipped cards, there's actually a solution. And how am I going to do that? So the verifier is going to challenge me. He's going to pick at random one of these constraints, let's say this middle column here, and he would like me to convince him that under the corresponding cards, there's actually all the numbers from 1 to 9 like there should be. Now, one thing I can do is, of course, simply flip the cards and show this to him, but this would already reveal at least a little bit about my solution, right? And I don't want to reveal anything. So I'm going to do something else. What I'm going to do is first take these cards, and now I'm going to shuffle them at random. Okay, I'm going to change their order at random and only then reveal them to the verifier. And now the verifier is really going to check that all the numbers are there between 1 to 9, and if so, it will be content and accept. Okay, so let me give you some intuition on what's going on in this protocol. So first of all, it's pretty clear that if the prover actually had a solution, me in this case, then I can pass this verifier challenge always. Okay. Now, what if there's no valid solution to the puzzle? Then the point is that there's at least some constraint, right, that is not satisfied. For example, this square here in red, where the number 3 appears twice under the flipped cards. Now, if the verifier happens to choose this constraint, then it will catch me. It will know that I'm cheating. So at least with some probability, the verifier can catch the prover if the prover is cheating, and you can actually increase this probability as much as you like, say to 99%, by simply repeating this challenge and response phase. Okay. Now, the last thing I want to convince you about this protocol is that it doesn't really seem to reveal anything to the verifier. In what sense? If you think about what the verifier sees in this protocol, it only sees the numbers it actually expects to see in any valid solution appearing in some random order that has nothing to do with my own solution. Okay, this is something that he could have, done himself. Take card between 1 to 9 and just shuffle them together. The last fun fact that I want to mention about this protocol is that, quite remarkably, it turns out that if you can prove Sudoku in zero knowledge, like we just did, then you can actually prove anything in zero knowledge. It is what we call NP-complete. Okay. So the way that I described this protocol was pretty physical. I used cards, and in reality, we're going to run a digital analog of this protocol over the internet. And I won't give you the details, but roughly speaking, instead of flipping cards with numbers, we're going to encrypt these numbers and send the encryptions. And other than that, the protocol would look pretty much the same. The verifier will give us a challenge, and we're going to open, maybe decrypt, some of these encryptions. Now, how do you formally argue that such a protocol doesn't reveal anything? So the idea here is to show a process that can really simulate from scratch whatever the verifier learns. And if you can simulate from scratch, and it's really warp scratch, it really means that the verifier learns nothing. And to do this, the simulation process will somehow internally run the verifier and try to generate a conversation that looks like a conversation with the real proof. Now, of course, the difficulty here is that unlike the prover, the simulation process doesn't have a solution, right? It starts from scratch, as we say. But here's a useful observation. If we somehow knew ahead of time what the verifier challenge is going to be, which constraint is it going to pick, then we could actually sort of cook up our encryptions, our flipped card, so that they will only satisfy the verifier constraint. And perhaps, in other places, they won't satisfy the constraints, but it can anyhow not tell, right? Because these cards are flipped or encrypted. So in this case, the challenge will come later and we'll be able to answer it correctly. Now, the simulation process in general cannot predict what is going to be the challenge, but it turns out that what you can simply do is just try to guess. So the simulation process guesses ahead of time, then it cooks up these cards or encryptions and sees if it got it right. It gets the verifier challenge, and if it got it right, then great, it can simulate. And if not, it is simply going to try again. It's going to do what we call rewinding. It's going to run the verifier again from the start and get some other challenge, try to cook up things, and see if it can succeed now. And it turns out that you don't have to do too many trials until eventually you'll manage to simulate successfully a conversation. Okay. So what goes wrong when the verifier is quantum? Let me at least give you some intuition. So the point is that quantum verifiers have internal quantum state, and quantum states turn out to be pretty volatile. In particular, whenever you measure even parts of a quantum state, let's say you look at the verifier challenge here, then this really disturbs the state. The state really changes. And what this means is that the simulator can no longer rewind like before, because if it's going to rewind, it's going to reach some different initial state. And the simulation won't really look like a real conversation anymore. And this makes arguing zero knowledge in the quantum setting much more difficult. Okay, so not all hope is lost. Let me tell you just in a nutshell about some advancements on this problem. So already back in 2006, what was showed that some classical zero-knowledge protocols can actually be proven to be secure even against quantum attacks. This, of course, requires a completely different analysis. And it also has some caveats. For example, either the cheating probability is very large, or it requires many rounds of interaction between the prover and the verifier. And very recently, together with my student, Shmueli, we managed to remove this caveat. We constructed a completely new protocol. And in order to do this, we actually had to come up with completely different quantum simulation techniques. And this has already had certain implications to other quantum secure cryptographic objects, such as multi-party computation that Juan talked about, etc. Okay, so I'm not going to be able to tell you about these protocols. They're actually quite complicated, but I would like to end by telling you that there's still a lot more to be done. There are interesting problems here. So first, the new protocols that we've constructed rely on relatively heavy tools like fully homomorphic encryptions, and in particular, the protocols are relatively inefficient. Second, we only know how to achieve a very basic form of security in the quantum setting, whereas in the classical setting, we can achieve much stronger security, for example, when protocols are concurrently run over the internet, which is a pretty natural setting. And lastly, let me say that, I talked about classical protocols that achieve quantum security. And I think that a fascinating question is whether we can actually use quantum protocols where the interaction in the honest protocol itself is quantum in order to do better. And I think this is a fascinating question. And I'm working with my students on all these questions, and I'm inviting you to think about them as well. Okay, so thank you very much.
Great, thank you, Nir. Really impressive the way you explained it. Can you maybe refer? We have in the cyber arena the very I would say trendy term of zero trust today that we take as kind of a idea of how to protect networks and organizations which are not that we don't know a lot about them, and we actually cannot be sure that any basic parts of them are really safe, and we try to develop ways in order to protect without any assumptions that we can trust
right.
things. So how I mean, if you think how the theory or the research that you run in a way based on kind of a similar way, so can you say a few words about the way?
Sure. Yeah, that's actually a great question, and it's always in the background of cryptography. So ideally, we would like to do things without trusting anyone, right? We'd like to achieve this miraculous zero knowledge property without trusting in no company or no trusted party. I don't know who I can trust. And this comes with a cost. So for example, the protocols that I described do achieve this. You don't have to trust anyone, but you do need some interaction. And for some applications, for example, if you think about many blockchain applications, interaction might be prohibitive. Okay, we really want to sort of like have proofs that we can write down on the blockchain. And you can show that this is something that you cannot do without any trust at all. You have to trust, to have at least minimal trust. So there's always this tension between what kind of trust you're willing to assume to what are the features of the protocols that you're going to get.
Mm-hmm. Great. So thank you very much for this insight of and the entire talk. It's a pleasure to have you here.